So let's go over the rules for reading bond line structures. So each corner or endpoint represents a carbon atom. So if we look at this first example, there's a carbon atom here, 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 and here. So also if we look at this alkene, this double bonded structure, there's a carbon here, 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 and here. And then finally, there's a carbon at 1, 2, 3, and 4. The zigzag format, this format here, is fairly accurate in representing bond angles for sp3 and sp2 hybridized atoms. But for sp hybridized atoms, such as carbons 2 and 3 over here, you want to show a linear straight line format. Notice the hydrogen atoms bonded to each carbon are not drawn. So how do you figure out how many hydrogen atoms are on each carbon? It's just a matter of deduction. So you know that carbons want to form 4 total bonds. So you look at the number of bonds that are represented, and then you add the appropriate number of hydrogens to get to 4. So if we convert this structure to here, we do so by first adding in our carbons. And then notice with the carbon on the left here, it just has 1 bond shown to the carbon to its right. So it wants 4 bonds total, so it must need 3 hydrogens. Now what about the carbon double bonded to the oxygen? It already has a total of 4 bonds, 2 to the oxygen and 1 to the carbon on either side of it, so it's good. What about the carbon highlighted in green? Well, the bond line structure indicates 2 bonds to the carbon on either side. The hydrogens are omitted, so you would add 2 hydrogens to get to a total of 4. Same for this carbon, and for this carbon it would be 3 hydrogens. So soon this will become second nature to you, and you can just look at a bond line structure and know and understand how many hydrogens exist but just aren't shown. So for practice, why don't you try identifying the location of the carbons and hydrogens in all of these molecules, and then you can pause the video and check back and see if you had it correct. Okay, so let's start with this one. So there's a carbon at the end of each stick and at the intersection of lines. So there's 1, 2, 3, 4, 5, 6 carbons. And then we want every carbon to have a total of 4 bonds. So that would require 3 hydrogens on this carbon, 2 hydrogens here, 2 here, 2 here, 2 here, and 3 here. And again, you're not going to draw in your hydrogens all the time. This is just to help you understand where the hydrogens are that aren't shown. Soon it will become second nature to you. So there's a carbon here. So at every endpoint, at every intersection. And then if we start with the carbon on the left, it just has 1 other bond shown, so it must have 3 hydrogens. Same with this carbon. This carbon must have 1 hydrogen. This has 2, 2, 3. Okay, over here we've got carbon here, 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 and here. And then we can add in our hydrogens to get to a total of 4 bonds for each carbon. Okay, and then finally the last one. So we've got carbon here, 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 and here, here, right here, all along this ring, and then at those ends of those sticks. So we've got a lot of carbons in this, and now we just need to add in the hydrogens. So this carbon is going to have 2 hydrogens. This carbon will have 1 because it has a triple bond to the other carbon, so that's 3 out of the 4, so it just needs 1 hydrogen. This carbon isn't going to have any hydrogens because it's already triple bonded to the other carbon and single bonded to the one above it. This carbon also won't have any hydrogens because it already has 4 bonds. This carbon won't have any hydrogens because it already has 4 bonds. This carbon will need 3 hydrogens, as will this carbon. I know this is getting a little crowded. These 2 carbons don't need hydrogens, they're good. This carbon needs 2, this needs 1, and then these need 3. So what you're looking for here is first to identify where the carbons are, then make sure that each carbon has a total of 4 bonds. If 4 bonds aren't shown, you make up for the lack of bonds with hydrogens. So if you're given a Lewis structure or a condensed structure, you must also be able to draw the corresponding bond line structure. So rule number 1, sp2 and sp3 atoms should always be drawn in a zigzag format. Rule number 2, when drawing double bonds, draw them as far apart as possible. So this is much nicer than this. Remember that this carbon is sp2 hybridized, so the bond angles should be 120 degrees, but this drawing does not accurately show that, so this one is not right. When drawing single bonds, the direction in which you draw them is irrelevant, so this structure is the same as this because these single bonds can freely rotate. Rule 4, any atom other than carbon and hydrogen is indicated, as well as the hydrogens attached to them. So if we convert this structure to a bond line structure, we still draw in the oxygen and the hydrogen bonded to that oxygen. And the cardinal rule, number 5, never draw more than 4 bonds to a carbon atom. That violates the octet rule, which is an absolute rule for second row elements. Now let's practice drawing bond line structures. So we have a condensed structure here. We have 3 carbons followed by an OH. So that's going to look like this. So each intersection is a carbon, and then the carbon on the left would have 2 hydrogens, the next carbon would have 2, the next carbon would have 2, just like that. But just to draw the bond line, you omit the hydrogens and the carbons. Now let's try the next example. So to convert this compound to a bond line structure, we do the same thing. So we've got 1, 2, 3 carbons. So 1, 2, 3. I'm using the zigzag, and then I'm going to draw in my nitrogen atom and the hydrogens attached to it. A lot of times bond line structures are drawn, but not all of the lone pairs are drawn. So it's important to be able to identify lone pairs. So the way you do this is if you have a bond line structure and you have an atom with no formal charge, in the next chapter we'll talk about formal charge. What you want to do is figure out how many valence electrons it has. You can do this by just looking at the group number in the periodic table. Then you count up half of all the electrons in its bonds. If the number equals the valence number, you're done. If it's less than the valence, then you add lone pairs to reach the valence. So if we try this with ammonia, NH3, nitrogen has 5 valence electrons because it's in group 5. Here it has a total of 6 electrons in all of its bonds because it has 3 bonds and each bond has 2 electrons. We divide that by 2, which gives us the number 3. Therefore, it is short 2 electrons from its valence number of 5, so we must add a lone pair to the nitrogen atom. Let's also try that with water. So water, the oxygen atom has 6 valence electrons. Here, there's a total of 2 bonds shown, which accounts for 4 total electrons. which when divided by 2 gives us the number 2. So oxygen is short 4 electrons, so we have to add 2 lone pairs, just like that. Let's practice this. So let's add in the lone pairs on the nitrogen and the oxygen, and then go through and add in all of the hydrogens. So first let me reiterate where the carbons are. So they're at each endpoint and intersection. So that's where all my carbons are. I'll go ahead and add in the hydrogens, and then we'll look at the lone pairs. So the carbon on the left has 1 bond to another carbon. So to get to 4 bonds, we need to add in 3 hydrogens. Same with this carbon. The next carbon already has 3 bonds shown, so it just needs 1 hydrogen. This carbon is missing 3 bonds, so it needs 3 hydrogens. The carbon bonded to the oxygen already has 4 bonds, so it doesn't need any hydrogens. And then finally, this carbon on the right just has 1 bond shown, so it needs 3 hydrogens. Now let's look at the oxygen atom there. Oxygen's in group 6. It has 6 valence electrons. Half of all the bonding electrons shown, because it has a double bond, it has 4 bonding electrons. So half of that would be 2, meaning it's missing 4 electrons, so we can add those as 2 lone pairs. The nitrogen shown here has 3 bonds. It's in group 5, so it has 5 valence. Half of its shared electrons is the number 3, so it's 2 shy of the 5. So we need to add in 1 lone pair on the nitrogen.